All right, excited to start the hands-on session, which has been prepared by Dr. Merve Kaptan, who is a postdoctoral research fellow with our group and is running several projects. One is with myelopathy study, spinal cord functional MRI and motor tasks, and then really working a lot on structural imaging analysis and improving diagnosis and understanding of degenerative cervical myelopathy.
Thank you. So thank you everyone for being here. This is supposed to be a very interactive session. Interrupt me at any time. So at the beginning, I plan to go over our processing pipeline, what we are doing, and then after that, we can go over the small mini tutorial, and starting from how to even download Spinal Cord Toolbox and SSL and so on. We can go over that and try to figure things out together. And also I have a lot of colleagues that can help me on that too. So don't be shy, ask questions. A little bit about me, just briefly, I did my PhD in Max Planck Institute for Human Cognitive and Brain Sciences. My PhD was mostly focused on only focused on spinal fMRI. I position from the user perspective, I'm not an MRI physicist, and also from analysis, and I use resting state data as well. And I'm doing my postdoc here at Stanford, and as Ken said, I'm working on different projects, including now the corticospinal fMRI data. And today, the task we are going to be using is collected by Valeria and Sandrine, so I have to give credit to them. So this is, you can find the original publication here. I think I already have sent it to you, but if you don't find it, please ask me. And here in this task, what the participants were doing, these are all healthy participants. So they were doing is that they have a dynamometer in their hand, and they see this small bar on the screen, and basically they try to, by using their force, they try to bring the dynamometer, so basically using their force enough to squeeze the dynamometer, and they get visual feedback with the bar, and then then they have to use different, basically different forces to elicit this visual feedback. And they do this in a block design and different with parametric modulation, so low, medium, and high condition, and then rest in between. And today we will be looking at one of our subjects and do a task where they use absolute force. So basically, we didn't change it for each subject. Everyone was given the same height of this white bar, and they try to match it with their force. And I would like to give a disclaimer before I start. So there's actually a very nice Turkish proverb that I really like. And I know it's a debate between Turks and Greeks, but we also love yogurt. And we have a saying that literally says every brave man has their own way of eating yogurt, which means everyone can do things differently. And this especially applies very well to spinal fMRI processing. Every group kind of does their own thing. During my PhD, my supervisor was telling me, you should do this like this. And I was seeing other things in other papers. And I'm like, okay, and one is not necessarily incorrect, and the other one, like, we can't definitively say, this is the correct way to do it. You should do it, the pre-processing as I show it now, or as our group is currently doing it now. However, there are some practices that are way better than others. And one is that because they are reproducible, more reproducible, less error prone, and much less subjective. And this is why I really would like to convey today. And let's look at the workflow. So let's imagine Christine, who talked about corticospinal fMRI acquisition, and she is collecting corticospinal fMRI data at the scanner. And this is I would say this is the workflow that she can adopt. So as you know, everyone's institutions are different, but I assume mostly from the user perspective, unless you are physicists who are really into MRI physics, we get the DICOM images from our institutes, from the scanners, and then we convert them to MIXI format. And this is with DICOM, we use DICOM to NIH for that. And the most important thing, in my opinion, is to first look at your data. Look at what comes out of DICOM to MIXI conversion. And for that, there are really great open source tools. One of them is FSLIs. I know some people call it fossilized, but I really don't like calling it that. I prefer FSLIs. But no matter how you call it, you will find the tool. So yeah, it's very important to look at your data. And then how do we name our data? So that's actually a very important question, especially if you want to share it with someone else. I can name my data however I want, right? I can name my data version 2, my data version 3. But obviously that would be very terrible for also reproducibility purposes. Also, if I give you the data, you would have to ask me so many questions. This is why actually people mostly from Stanford came up with this. It's a big community effort, but mostly driven by Stanford researchers Russ Poldrack and his team to come up with an efficient and reproducible way to organize the data. And I will go into that. And then how do we manage our processing scripts, and how do we even do this naming to bits? You can do everything manually, but again, it's much less reproducible. The more you script, the more you have everything scripted and put it on GitHub, it is more reproducible. And once you want to go back to your data in 3 years, you can still be able to do that. And that being said, this is a learning curve. When my PhD supervisor first asked me to do it, I really didn't want to do it. I find it like so much of a hassle, but once you get into it, it really helps. So I just want to briefly mention bits. So as I said, it's a community effort, and it's really a way of naming organizing your data that it's then understandable to other people. And GitHub is a version control software. So instead of you having a lot of local copies of your pre-processing, you can have everything centrally. And I believe you don't even need to use GitHub a lot of capabilities. You don't even need to use it to the full capability like a software developer. If you just have it on somewhere that you know that's your final version and someone else can see it, I think that's already a great start. So let's look at the data that Christine acquired with her corticospinal fMRI sequence with the force matching experiment, and how do we basically would organize that. So as you can see, the bits data is organized in a way that there's source data that you put your NIFTY files, and then this is the data that you don't basically touch, and then you put all the derivatives of this into derivatives folder. So there's a functional data folder, and for corticospinal fMRI, basically, as Dimitri mentioned this morning, we separate the spinal cord and brain, and we put them in different sessions. Although they are acquired in one session, this is the best way to kind of adapt the bits to our needs. And then here you can see how we organize the anatomical data. This is our T2 weighted images, and this is our T1 weighted image, and you can see that there is this is the sidecar JSON file. So if you send me this data, I will be able to look at the JSON file and see some parameters that are of interest to me.
Yes, so do you have like longitudinal data? Because like it says that it's like session, right?
Yes.
But we have like more than 1 or 2 sessions.
Great question. So for our case, I would do stage 01 spinal cord, stage 01 spinal cord, stage 01 brain.
Yeah, you're allowed to call the folder anything.
Yeah, as long as you maintain this structure. Sandy, did you have a comment? Oh, I thought, okay. I don't even like what I said. So there are a lot of analysis tools, and we try to use the open source ones. And there are, as I said in the beginning, there are different tools. Everyone can do things differently, but I think using the open source ones helps. And we use FSL for pre-processing the brain data and also further analyzing our spine data. And we use ANTS for normalization tools. And for the spinal cord analysis, we rely a lot on spinal cord toolbox. However, as you have seen also on the day one, the spinal cord and the brain tools are evolving. So now, for example, in day one, Julian mentioned the new motion correction method that is coming up. So maybe we will change our pipeline to adapt to that. So this is not a static pipeline. With every improvement, we improve basically our processing script as well to optimize our results. I want to give a quick overview of the steps. So for the brain, we start with the anatomical data processing. We do skull stripping and we segment gray matter, white matter, and CSF. And then we continue with the functional processing. We do the motion correction. We get the outliers, like the spikes. And then we do top-up correction. We do physiological noise modeling and normalization. And then we go into the first level analysis. For the spinal cord, we do anatomical data processing as well. So we identify disc labels, or now we are actually identifying nerve roots, and we segment the spinal cord. We normalize our T2 weighted images to the template, and then we continue with the functional pre-processing. We try to keep it as similar to as brain because we want to look at the interaction between them. So we don't want to do apply hugely different pipelines between those two. And then ultimately we continue to first level analysis. And I will focus more on spine. I think it's more interesting and I like it more, but we will quickly talk about the brain as well. And if you are interested in spinal cord, so all of our tools, basically most of our tools come from Spinal Cord Toolbox, and I cannot emphasize enough that you should join the Spinal Cord Toolbox course. It is free and online, so you can, just scan the QR code and sign up. So they will cover most of the things I'm covering here in much more detail, and it's better to hear from developers than me as a user. But I will quickly go over our pipeline, and I stole some of their slides. So basically, what we want to do for an fMRI analysis, bring our data to template space, because everyone's spinal cord is in different spaces, and we want to find like the group level activation, and this is why we need a template. And thanks to Spinal Cord team, and they developed this PAN50 template that's openly available, which you can use, and it has a template of the full spinal cord or almost full spinal cord, and then also it has white matter, gray matter, and CSF templates too. And basically what we want to do with our anatomical pipeline initially is to bring our anatomical image to the template space. And Sandrine also mentioned that in her talk, but in order to do that, we first identify the spinal cord. This is the segmentation. And then we can label the vertebra, but we might also do different things. I will talk about that. Then this is used to straighten the spinal cord. And then there are affine transformations that really match this vertebral levels between native space meaning the subject space and the template, and then non-rigid transformations that match the cord, and then they concatenate these working fields, and this way you get template transformations to template and backwards from template to the subject or native space. And the first step is to segment the spinal cord. So this is the latest segmentation that I would recommend. It is contrast agnostic and it works very well or on our T2 weighted images. And this is how you would call the command. Basically, it's STT deep seg, spinal cord, and then this is our T2 weighted image. And then this would be our output, which will be in the derivatives folder, which I didn't put here because I wanted to keep slides clean, but we can go over the pipeline. And how does this look? So this is one subject, specifically the subject 43, and then this is the automated segmentation. So you can see it looks great. I'm going through the slices. Yeah, as you can see, it looks really good. So no need for manual corrections. Looks great. Although we know that automated tools work well, it's very important to still check your data. And then actually I talked about how we bring our anatomical image to template space. And previously we were identifying these discs and then using that as a marker to bring them to template space. But now Sandrine and Jan came up with a very cool methods that allow you to segment the rootlets basically. And then this is a deep, so you can actually use rootlet seg, and it's a deep learning based segmentation of nerve rootlets and nerve rootlets, and can be used to estimate the spinal levels, which actually can result in better group activation map. I will give you a sneak peek on that. So how do we use that? It's again under the STT deep seg command. We just call the rootlets. So there are a bunch of options for the deep seg, and this is the rootlets one. This is the input, and this will be our output. And this is how it looks on our subject. So this is, we acquired 0.8 isotropic images, T2 weighted, and I would say the rootlet segmentation works pretty well on them. This is from the spine generic T2 weighted acquisition. As you can see, I try to put my cursor here. Yeah, the rootlets are nicely identified. And you can always go back and manually correct if anything doesn't work. Then basically we do this level-based alignment. So instead of aligning the disc, we align the spinal levels. And this is how the registration works. And then you can see the registered image in the PAN50 space. Yes.
Can I ask a question in between?
Yeah, of course, I would love it.
Yeah, for you, so how accurate do you need to, or do these rootlets need to be segmented for the labeling to work?
Since, I mean, the more you rootlet segmented, this is like the perfect case that you want. If you have really all the rootlets you can see from the spinal level. But if you go to the other side, Merve. Yeah. But there is like this first step. So we have the rootlets, and I compute the center of mass of each rootlet. So if, for example, you would have like a compression or like a CSF flow artifact where you'd lose signal, you could also just manually select the center of that level, and that would be used in the first step. And there is also a second refinement that uses this segmentation, but if like they wouldn't be, or there are some of them that are missing, they would not be aligned necessarily, but that is okay. So there's like a two-step. There's like the first gross alignment of the spinal levels, and then there's this kind of refinement, really using the segmentation of the rootlets.
Can I?
Yes, of course.
So on the right, there are these gaps between the rootlets, the different levels. So if you see an activity right there in between two, so how do you label those levels?
Well, I think that's a question we're also wondering, in the sense there's the thing that the rootlets we cannot see exactly. I think at the upper cervical level, rootlets are pretty parallel, perpendicular to the cord. So there's a bit maybe less gap, but the further you go down, you cannot really see the rootlets dorsal entry because it's just really over the cord, and we don't have a contrast between rootlets when they are really like on the cord. So I think that's why we can have this kind of maybe gap. But for example, I would like assume if, for example, above C8 below, and also this is just one slices, but these are like 3D structures. So you can look also at the other coronal slices because they will probably enter a bit more up if you go the red one at C8. But I would probably assume that a bit above C8 is still C8, just because the rootlet entry zone, I cannot see it.
And this is how we would call this command. Basically, it's SCT register to template. And this is our input T2 weighted image. This is our segmentation. And you would then call the L rootlet option. And as this is the segmentation that we got from the previous step. And our contrast is T2. And this is here, you can see the PAN50 template. T2 weighted PAN50 template, and this is how my image, our subject image, would look when we bring it to the template space. Again, it's always a good idea to check the registration work well. And why do we want to do rootlet-based segmentation? Segmentation and registration, and exactly because of that, this is a sneak peek into Sandrine's recent results, and you can see that this is the group level activity maps across 40 subjects, and you can see that if we do a rootlet-based registration at the group level, we see much stronger activation and much stronger and consistent activation compared to traditional disk-based registration. And you might be wondering, okay, what if I can't see rootlets well in my anatomical image? Then you can always use the disk labels, and I put that command here. You would just segment, label the vertebra, and this works well automatically as well. And again, you can always do manual correction, and then instead of giving the rootlet as an input file, you would just then give the disk file as an input. Just change the input here, and then you would use this to register our images to template.
This differs across subjects. Would you recommend mixing these up or sticking to disk labeling for a group analysis? If just some of the subjects.
Personally, I wouldn't mix it. Also, it's hard to report in the methods section of a manuscript, but I don't know if you have any experience on that.
I would not, I don't think I would mix, and even if there's a subject that you don't see it well, probably you can still manually label some levels. Also, you have interest in possibly specific levels for your task. So maybe if you're missing the first spinal level, like C2, it's not, like you don't see it, that's okay. It will just not be in your registered field of view. But to be honest, like if you go to the slide before, on the right is just the average of the anatomical image. And when you register with disk, you see that there's kind of no alignment of the rootlets compared to when you align with the rootlet. So I think just the anatomical result is kind of convincing, but yeah, I would not go and mix it all up.
Okay, so now we talked about spine anatomical processing. Do you have any questions before we jump into the functional? Okay. So its functional processing is to create a denoise 4D time series image so that we can do our first level subject-based analysis, which we can then use to look at the group level activation maps. And this is, as we talked throughout the whole session today, it's very important how you process your data. It's also very important how you acquire your data, but we are focusing on pre-processing here. And this is our 4D time series data. So as I said, I would just open it and look at it in FSLI just to see how it is looking. Is that, see here, there are some nice artifacts here, but okay, they are not going into the spinal cord. You see a little bit of motion, but overall, this doesn't look necessarily so concerning. You can see the signal dropouts are more amplified towards the lower part of the cervical spinal cord.
That artifact's, I think, just the video, right?
Yeah.
The lower left.
I think it's like set.
Good, or just no, with your hip play. There's a flicker there. That's not in the time series. Yeah, you're good.
Okay. And then the first step is to do the motion correction, which is specifically important for the spinal cord. I mean, it's also important for brain, but spinal cord is a very small and delicate structure, so we really want to do the corrections as much as possible. And in order to do that, first we create a mask basically around the spinal cord, because we don't want to motion correct and use all these structures outside the spinal cord as for alignment. So we create a spinal cord mask, and we don't need to do this manually. We can actually use another DeepSeq tool that works well on EPI. So this is STT DeepSeq SCEPI, and then you can use this to get the spinal cord, and then you can then use this with the STT mats and dilate. So this will give you the spinal cord, and I will show it to you in a second. And then you can dilate this and get a spinal cord mask that is covering a little bit more than spinal cord, because this is what we want to use for our motion correction. And we do two-step motion correction here, and we have a specific code for that. That is, I believe, from Kant's PhD. And basically, we use the important thing, and the script is available to you, but the important thing for you to know is that we are using FSL for motion correction. We use specifically the tool FLIRT, and then we do 2D motion correction. So we don't do 3D, it's 2D slice-wise motion correction. So first, we get our raw time series, and then get the middle volume, and motion, just do the motion correction on the raw time series, and this will be outputted as MC1. And then using this motion corrected time series, we take the mean image, which gives a better reference, and then we motion corrected our time series to this to get a little bit better image quality. And here you can see I'm showing the motion corrected mean image, and you can see that this is the raw, this is the motion correction. You see that actually it worked quite well. You see the time series of like raw mean is very, very blurry, and after the motion correction, it looks much more crisp. Yes.
So the option that here is blurred. And I know I use that. But isn't there an option called MC blurred in FSL, which actually does the motion correction? Is actually for it. And
Yes, there's MC Flirt. I don't remember if there's a 2D option in it.
it doesn't have that. And we also ran into that problem. That's why I'm asking, because this function is normally used for the registration purpose on the motion correction.
Yeah.
So you think that using flirt for the motion correction is a good choice, better choice than using MC flirt?
Well, just because MC Flirt didn't have a 2D option, I also don't think it allows a mask to be input. I don't remember the options, but this is essentially using Flirt across every volume, and it's wrapped into a function, a bash script function. It seems to work well. This is another area that I think needs optimization, is motion correction, and it's also unfortunate because it's one of the first steps that we do, and I think we can do it better. So excited about hearing about the deep learning option that might be available in the near future. But it works fairly well, I feel.
Also a way of
Yeah, exactly.
Yeah. No. I think McFlirt uses Flirt. If I'm MC Flirt uses Flirt underneath.
Yeah.
So where do you specify the degree of rotations in
The 2D part.
So what does 2D mean?
And allows translations and XY translation and a rotation from line C.
That's it. So it's rigid. So 2D means XY, like TX, TY, and RZ.
Yeah. And I used SCT fMRI Mocha, for example, which also allows the 2D option with some constraints. I think based on course curvature, and that worked well for me too. Yeah, that's from the SCT. I think one can also play around with different options.
False ants, right? So yeah.
Perfect. Maybe also one point, like since this is masked, sometimes if you have a subject that has a lot of motion, maybe your mask will not be large enough. So this is something to check also for, and maybe also one of the limitations.
Yeah, so. And then one thing again to look at if our motion correction worked well or not, to look at TSNR, and you can use SCT for that. So if we use the SCT fMRI compute TSNR on our motion corrected time series. So as you can see, we tried it in the derivatives folder. So these are all pre-processed data. But even within the derivatives folder, we try to keep a consistent naming. And this is the motion correction step 2. We call it MC2. And then you can just look at the TSNR. So this is from 10 to 30. As you can see, the lower slices doesn't have a lot of high TSNR. But this is what we expect. It looks within our expectations. And then we find the yeah.
Can I ask a question about the TSNR, representation, like in publications? Some people represent the TSNR without much without interpolation with trilinear, because the trilinear interpolation will reduce the noise and will boost the TSNR. So we get a false representation of what's the effective SNR of the data that's supposed to represent the inherent noise. So do you have any thoughts and recommendations about using nearest neighbor interpolation after motion correction just to show the TSNR comparison before and after MoCo? What are your thoughts on that?
I think you are definitely right. This is a little bit of a biased representation, because if we use interpolation, especially twice, then we are really boosting our TSNR. So I think that would be maybe good to show raw MoCo with nearest NM, and then maybe the whole denoised TSNR without smoothing.
Because it's like, speaking of harmonization and comparing like protocols, some if people compare stuff on TSNR, but TSNR is not computed in the same way, that's not very helpful. Because today we've seen SNR ranging from 10 to 50 or something.
Yeah, we want to be able to look within the chord, right? So I guess you have to. I think motion correction seems like a necessary step, because the raw time series it's not going to be maybe as helpful. But you haven't been reviewer number 2, I guess, and said recompute everything, your TSNR things. But it's a good point. And if a reviewer asked us, we would do it. But, yeah. And then we actually save the transforms for each volume? I think so. No? Maybe not.
We do.
But yeah, we could use those easily to do both. Yeah. Good point.
But yeah, that's a very good point. I think also being transparent is very important. Like exactly saying what TSNR we are reporting. And one good thing is that if the data is online and public, one can always check the data quality. And basically then we use FSI motion outliers to identify the motion outliers, as the function name suggests, and we use the device function with a device calculation with a mask within the spinal cord segmentation, and this gives us basically an outlier text file which we can then use within our GLM, so that volumes don't contribute to our GLM analysis. And how does that look like? So this is a representation of the text file. So here you would have your number of volumes. So you would have, and this is the number of outliers. So this will change for every subject. So basically this means that this volume will be flagged as outlier, and then this volume, and so on. And which then you can feed into your first level analysis. And so another question is to segment the EPI. And how do we do that? Previously, that was, I would say, there was automated tools, but mostly more manual. Now, actually, I was also involved with this work, so I'm very happy about that. Rohan led this work, and we developed a tool to segment the challenging EPI. So it's SCP DeepSeg SC EPI. So we get our mean motion corrected image, and then using one of the functionalities of SCP DeepSeg, we can segment the EPI. And this is important because we later then use this for normalization, and also if you want to report the TSNR values, people are mostly interested in the TSNR within the spinal cord, and you need a spinal cord mask to do that. So this gives you a nice functionality. And again, obviously nothing is perfect and every fMRI sequence is different. Please do manual corrections if necessary. And this is our segmentation for this subject. I would say, I don't know, I might be biased, but this looks pretty good in my opinion. I wouldn't do manual correction, on this. So let me show it to you again. Maybe here, small touches here and there, but I don't think it's really necessary. And yeah, always remember to check the outputs. Even the tools are getting more and more reliable. And then,
Can I interrupt?
yes.
Okay. Just want to point out that the spinal cord contrast agnostic model for the structural imaging, and then now having EPI-SEG has like almost fully automated these analyses. At least, well, there still need manual touch-up, but it's a huge, it's really reduced sort of the cost of doing these analyses, because we could, spend hours coloring in these spinal cords. SCT prop-seg for a lot of our images had required like a lot of manual touch-up. And so one, thank you to Sandrine and Julian and your team. Thanks to Rohan and Merve for all the hard work putting into that, because it's super awesome. And it also is, they both are multi-site collaborations. So just thank you. Want to say that.
And why are we segmenting the spinal cord? Because then we would use it to bring our image to the template space. And this is again very important because we need the results at the group level. Everyone's spinal cord is different, so you can't just average the spinal cord of different people. You need a common template, and we need to bring our EPI images to the template space. For this, we use STT register multimodal, and as you can see, because the T2 weighted image is higher resolution, we bring so this is the T2 template, and this is the T2 template segmentation, which are available in SCT, and then we bring this template to our native space. This is the D destination segmentation, and these are the parameters. I think you can, again, there might be different sets. You can start with the recommended set of parameters, and then you can play around with them according to your data. This gives a lot of, this function gives a lot of options that you can play around with. And then we use, so if you now remember our anatomical pipeline, we use these words that we got from our anatomical pipeline that bring our anatomical image to template space. We use that verbs to initiate this registration between SCT template and our functional image. I know it's quite complicated, sounds complicated, but interrupt me at any point. So basically, this is our output. This is our functional image in the template space. And again, always check your data. It looks pretty good to me. And then the good thing is that we can also bring all these interesting templates to our native space. For example, let's say I want to calculate the functional connectivity between different parts of the cord within the native space. Obviously, with my EPIs, I won't be able to see the gray matter. Even if I see it, I would need to manually segment. Yeah, it won't be possible. But then using SCT warp template and the destination as my native image, I can warp all these templates to my native space and then use the templates in the native space, which would help with further analysis and also further denoising. Then we use this to create a white matter mask. So we use this basically because we regress white matter in our pipeline. Again, we heard some debate on that today, but basically we use the PAN50 white matter template, bring it to the native space, and then use this for denoising. And then we also create a CSF mask, and SCT has a nice functionality for that. For this, we recommend SCT prop-seg with the CSF option, and using the motion-corrected mean image as the input, and contrast would be T2 star. And here you can see the, is this a video? It's not a video. I just put one image. So basically you can see the CSF and white matter masks in the native space. So the white would be my CSF mask, and the pink is my white matter mask, and then I would get the signal from this and then use it for further denoising, which we will go into a little bit later. And we talked a lot about physiological noise, and spinal cord is very close to heart and lungs, and it's actually very important to do physiological noise modeling. Here you can see how the cardiac-related noise affects the fMRI of cervical spinal cord. And there's a lot of noise associated with cardiac and respiratory processes in the spinal cord, particularly with the spinal cord fMRI. And Gary actually developed RetroICore, and then which was then adapted into this nice graphical user interface or base command tool by John Brooks and his colleagues with the physiological noise modeling, PNM. So this is a functionality of FSI, and you can do it GUI based, which we don't recommend because you can always make errors. It's nice to script everything. And basically, we give the input physiological recording. So I have to mention that we really record pulse signal and respiratory signal during our fMRI experiments so that we can regress out their influence from our fMRI time series later. And then we give our input time series. And basically, this creates voxel-wise or slice-wise regressors for our fMRI time series that we can then use to denoise cardiac and respiratory processes. And this is how one would function it. Again, it's I'm not going into details of all the scripting, but this is the functionality of FSL. You can use POP and PNM EVs, which then ultimately creates this EVs. So you see this huge giant matrix. It's a denoising matrix, basically. And here you see all the EVs associated with physiological noise. Basically, all the 32, I think first 8 is cardiac, second 8 is respiratory, and then the others are their interaction. And we have the white matter and CSF signals, and then the 3 motion correction parameters. And we all regress this noise out from our fMRI signal. Basically, this is why we go through all this hassle of collecting the data and then, so that we can try to minimize their influence as much as possible.
My comment?
Yes.
And so the choices here are the default ones, mainly from Jonathan Brooks' papers, I believe, right? For number of cardiac, number of respiratory, and then their interactions. And then they also recommend using CSF. So that's what we did. White matter we included because Robert Berry included it in some of his analyses, and then we've included it pretty much since then. But it's not that we know that this is necessarily the best modeling of the physiological noise. So
yes,
that's fine.
How do you include the white matter in the
So basically, after bringing the PAM50 template to the native space, then I see the white matter was in the native space, and then I can extract the signal in each overall white matter, or if I want to do it slice-wise, for each slice, and then edit as a text file in the FSL feed regression. Basically.
Can we do slice-wise, right?
I think we do slice-wise for white matter. Oh yeah,
it's not mean signal.
Oh, you don't use them. Yeah. This is the first FSI mean tiers. I can't tell you the details. So we first take the first eigenvalue of the time series. Yes, and then you can just also script it so you don't have to go through the hassle of using the GUI each time.
But I didn't know that.
Oh yeah, it's inbuilt. So if you write a capital P and small nm, it should open this.
And what does it ask you to input?
So basically, it asks you to input your physiological recording, which I can show you after going through this session, but it would be like your cardiac data that you collected, your respiratory data, and the triggers, because this is volume-wise, right? So it needs to know know the volumes. And then usually, because we need to give the cardiac peaks, we do a step beforehand, which I skipped for this tutorial. We select the peaks, cardiac peaks, and then we select this option as pulse ox triggers. You need the slice ordering, slice acquisition order, and then how you want to name it, and then how many cardiac and respiratory noise variables that and interaction variables that you want to define.
How does this differ from the retroactive model?
This is based on retroactive. I think this is more wrapped in a GUI format.
You do this one or that one.
Yeah, the idea is the same. We just use the, I would say maybe the more easy functionality that's integrated within FSI. But this is based on the retroactive work.
And then what John Brooks pointed out as being the optimal, but it's several years, like 2000.
I think that's 2008.
Eight study. So there's probably we can do better job at optimizing sort of noise modeling.
And for example, we use 32. I know Dimitri's group, they use 18. Alexandra Tinnerman, they use 18. So instead of 32, I think one can optimize that as well, depending on how many, because it also affects your degrees of freedom, right? So, like, if you regress a lot of things, yeah. So, yeah. And I know, for example, Gergely is actually doing, they don't really do TNM, but they use a mask and then they take they do a PCA or COMP-core approach to define their. Yeah.
So all the movement parameters for each slice to be. So there are as many slices as you have so many components.
Exactly.
So 18 multiplied by the number of slices or whatever number of noise structures that you have.
Yeah, and then they're all converted into nifty files.
Yeah.
So slice-wise nifty files that are then used as regressors, and then FSL handles those pretty well.
So we already talked about this multiple times, but the white matter, regressor is very concerning to me, given that because of the draining bane effect, you might have a strong correlation with the task inside this regressor. So you're basically removing variants of the task that you're after. Yeah.
I know, for example, Christine doesn't like to remove it. Half my PhD supervisor was like, you can't remove it because there's a lot of partial volume effect. I know you tried removing and not removing it, and the results were comparable.
Yeah, I think it was just like it was on this data actually on 18 subjects, and like the group level was very, very similar. Yeah, there was not much. But I think, we could still do more tests of how it affects it.
That's already.
Yeah, but that's why, I think it was something I tested since it was not very conclusive.
That's a very interesting result to report, I think, in the publication, because people are wondering.
I think it's already, one of the reviewers asked, and I think you added it, right? Already to the publication?
So to add the result, it was not on the entire report.
Oh, I see, okay.
But we justified it.
Okay.
So that was this data?
Yeah.
This data. But I still have the results.
Is there any reason that you could do the segmentation for CSF instead of using the template? Like you are using the white matter mask from the template. Why not use that?
That's a good question.
That's a really good question, and I can't justify it right now. Why did we do that? Can Sandrine, why did we decide on that?
I would say that there are some deformation of the PI volume. You would have them for the chord because you segmented your chord and you registered, but the deformation that are on the canal, you don't have them. So that's what I would say.
You're not registering
That's
You're
registering the chord, and so there's.
But maybe on like an anatomical image, a T2 image, then you could do it. But it's just because of distortions.
Because we don't want to remove any signal from the chord as well, right? That's the.
And we use SC offset.
We use STT-PropSec.
It works pretty well. So,
Yeah.
do you know anything from outside the spinal cord, outside the skin that we live in? That the non-spinal mask also can be one of the reasons.
I think we haven't implemented that in our pipeline yet. Gary, aren't you using the external or no?
No, on CSF.
I think Molly Bright's group.
Yeah, non-spine mask. He created something like a non-spine mask and took 70% of the variance from that signal as a regressor.
I think Molly Bright's group is doing that, and she has some publications in human brain mapping, recent publications showing that the benefits of effects of external PCA. Yeah. But we haven't implemented it in our processing pipeline. Again, so many options and a lot of things to really systematically compare. And then, okay, so slice timing, another controversial point. So I marked it as optional. And why is this controversial? Because actually we are creating slice-wise regressors, and ideally you shouldn't do slice timing before creating the slice-wise regressors, because your slice-wise regressors in PNM really rely on how your slices are acquired, but we do it after we regress out the physiological noise to not break the basically the dependency between slice-wise regressors. And this is why you can see the input image is the motion corrected and then PNM regressed out image. Basically, so we do the PNM first, the motion correction first, and then PNM, and then if we do slice timing, we do only after the PNM. And then you get PNM and slice timing corrected image.
Well, why is that optional?
Oh, I said optional because I know, for example, John Brooks and Falk, my PhD supervisor, was very much saying that you can't do PNM and slice timing together.
But you're saying that you're doing like slice timing after PNM.
After PNM.
All together.
So pretty PNM, and then we were like, oh, we never did it, but then actually I think we can do it after PNM.
But why is that optional then?
I think because a lot of groups are not doing it, so I marked it as optional.
But what would be the right way to do it?
That's a really good question. I think one has to do a systematic comparison. But definitely this would be one of the wise ways to do it. If you are doing it, you should do it after PNM, in my opinion. But I also know from Ekhan's results that from Dimitri's group, they do it actually before slice timing. And I asked them about that, and they said they didn't see a lot of difference if you do it pre-slice timing and after slice timing.
It depends on your.
Yeah, short TR.
Yeah, it's been argument. It's not your.
Yeah. This is why I also called it optional.
This incorporation because.
I mean, to me, the decision should be based on the scientific rationale rather than the results, if it looks good or bad, right? And to me, the rationale makes sense that if there is slices were not acquired at the same time, and you're after, an HRF representation or task-based fMRI, then slice timing makes sense. The interpolation, though, is a valid point.
Well, I think when you say optional, you mean you're talking about when is the correct time to apply. It's not whether we apply it is optional.
I will be honest, I said better to reapply it is optional, but I know Gary said you have to apply it. Not applying would be stupid. So I know there are like strong opinions on that, but for my PhD data with 2.5 seconds, we didn't apply.
Well,
that might be wrong.
That may be wrong, but I'm asking what can be a reason not to apply it?
I think the reason might be the yeah.
You are introducing interpolation after interpolation. That you get one level of interpolation of things that you are doing, and how much you are willing to sacrifice the signal for interpolation and all the trade-off that you want.
But I think with a lot of PR, then it can be HR with PR. That could be a big problem.
Yeah, sure. Yeah. I agree with the long PR.
In short your, I would say up to 2 seconds. I think you might have more artifacts because of this than you actually improve the data. At least at the brain, we've seen weird effects if you do slice timing correction and the interaction with motion realignment
That's also
can
true.
be tricky. Because it's a bit like the chicken and the egg, right? You should do them ideally at the same time. There is no algorithm to do it at the same time.
And with the brain, you're doing 3D motion
Yes.
correction. Here we're not, just
That's
doing 2D, which also makes it kind of. And then also, there might be an error here that we also use a custom slice timing file with this because this is a simultaneous brain spinal cord acquisition, and that flag's not here for that. But we have all this on a GitHub repository, the actual code. Yeah. So just making a note.
And then basically we apply the warps. So because we want to bring our template space of our functional data to template space, we want to bring our denoise data to template space. We apply the warps to our for the denoise data to bring it to the template space. This would be the destination. This would be the warps that I got from previous steps. And here we use a spline interpolation. And then we apply smoothing, which obviously helps with our SNR. And we, as you can see, considering the structure and the function of the spinal cord and our data acquisition, we do anisotropic smoothing. So we smooth less in plane because we are interested in where the activity is localized in plane in the gray matter, and for the basically we smooth more across the Z dimension, which would be
So as discussed also today, why doing smoothing as opposed to acquiring bigger voxels, which gives you more SNR?
I guess the decision was, well, we want the smaller voxel, but we haven't. When we're trying to decide build the sequence, we haven't really thought about what are we going to downstream, what are we going to smooth it with.
That's what we are talking about during your talk, like we're trying different voxel sizes.
Yeah, and we want to do one by one, but because we also want to do multi-echo, and that will make it impossible. So, yeah.
And actually, I have a question here. Wouldn't it be an issue? For resting state, I think that won't be an issue because sometimes we don't want to smooth the artificially inflate the correlations between the ROIs. And would that be an issue for registration to the template? So if I want to bring this to my native space, and if this is already a few voxels, and if I already have this in 2mm resolution, this would be even, like I would have maybe one voxel for white matter, and I wouldn't be able to distinguish.
Well, the smoothing done after the registration, similar effect of introducing, a spatial correlation. So that's one, and also, the other point is that, there was a follow-up question is why are you doing the analysis in the template space as opposed to, I'm talking about first analysis.
Yeah, first level.
Why wouldn't that be done in the native space in order to, avoid introducing those interpolations.
Yeah, so that's a controversial thing. We do the analysis in template space because we want to smooth a straightened chord. Now, if you're suggesting not to do smoothing,
well, yeah,
then that might be something you don't need to do. But would it be? I think Merve mentioned this though. Like, let's say we had 3 by 3 millimeter in plane resolution. Not that we want to do that. That's you can't. Can you accurately register that to the template? You think? Or is it too low of resolution to register to PM50 template? And is there advantage like a 1 by 1 in plane resolution? You probably can more accurately register to the template. So spatial resolution could affect your ability to register the template. You think? I don't know.
Yeah. Yeah, since we are getting the voice method signals pretty smoothing. So I feel like we would lose this ability, for example, right? If we have really big voxels.
So you're doing the noise form.
Yeah.
Yeah, I don't know.
And then again, another important point. So I try to keep my ACT functions as simple as possible so that you can easily see instead of reading a lot of lines. But it's very important to do the QC. So this is why I put this nice reproducibility flag. So we want to be reproducible, and you should really use the QC functionality of Spinal Cord Toolbox, which allows you to go through this automated outputs in a very user-friendly fashion. So how would I do the QC? I have a small video. It's a little bit fast, but you can basically. So for this subject, you see, you can like go back and forth. So toggle the arrow to see how each step looks, and then you can easily flag them. So you can even see the output of motion correction. Instead of opening everything in FSLIs, you can really look at this nicely, and you can even share this QC reports easily with your colleagues, with your supervisor, and then I just select this as an example, and then you can basically download this file, which then you can automate your script, and then you don't have to write down, oh, I have to go back to this subject and manually correct it. You can basically have a fMRI file, which is like a text file, which you can then feed into your code and automate the whole processing. And basically what I really wanted to take out from my presentation, I know it was a lot of comments, a lot of input, especially for people who are new to spinal fMRI, was really reach out to people. I feel spinal cord fMRI community is quite open. Just ask how you did this processing, why did you do this, and if they don't respond, it's on them. And I added this slide today. I really recommend using the forum, and I will show examples from my experience with the forum, and please look at the years. So look at the year in 2019, when I was a newbie in spinal fMRI. I posted and I got an immediate response from Julian and his team. And then 2 years later, I have more, but I just found some examples. I again posted a question and I got a response from Julian. The response time is quite fast. And then recently I also asked the question, and then Julian responded to me. So basically, I really recommend, if you have a question, don't be shy, go to the forum and ask, and ACT team is really there to help, and they helped me throughout my PhD and also through my postdoc, as you can see.
I just posted a question and Julian answered already. Is there a bot behind that?
Yeah. So if there's one thing I want you to take from my talk, is basically try to do the reproducible practices as much as you can. Use GitHub, try to script everything, and use the SCT forum. And I will quickly, we have 15 minutes and then 1 hour to go over all the questions and try to download SCT and FSL. And I will quickly go over, no, not 1 hour actually. Oh, no. So they added 5 or 5? Okay, I will very quickly go over our brain structure.
Yeah.
It has, okay, 5:30, nice. We can also end early if you are tired, but yeah. And as I said, there's STT course as well, so for STT, all the STT functionalities, I really refer you to that. So I just want to give a brief overview of our brain pipeline. So for the anatomical pipeline, we, as I said, we try to really keep it to spinal cord pipeline as similar as possible because we don't really wanna, because we wanna really look at the interaction between them, and we don't wanna apply vastly different steps that might create a confound. And we use ants for brain extraction. Sometimes it works out, sometimes it doesn't. So again, you always have to check your data. I think ants works well, better than FSL. In some of our data, I've seen that sometimes HPM works better as well, but you really have to see. And then we use, again, this is all FSL-based tools. We use the fast segmentation to obtain CSF and white matter masks. And this would be the fast function from FSI. And so I just cropped the face for PHI reasons, but this would be a complete image. And this is basically our T1 weighted image. This is the brain extracted. And this is the white matter and CSF segmentations in the anatomical image. And why do we use that? Similar to spinal cord, we want to bring this to the functional space and then regress that signal out. And I will quickly go over the brain functional pipeline. So basically, an important thing to do is the motion correction. So basically, we use the middle volume as the reference volume. And for brain motion correction, we use McFlirt. And you can see people's brain move much less. Actually, this is a 4D video, but it's hard to see the movement. Brain moves much less than the spinal cord. And yeah, as I said, always look at the outputs of each step. And then we also calculate TSNR. And then we extract the brain to get rid of the skull. So for this, you can use FSR's BET functionality. And then, to extract the brain. And then for this, we use FSR's BET functionality. And then we binarize this segmentation to get a binary brain mask in the native space. Again, we calculate the motion outliers, as I mentioned, similar to the spinal cord. And here we do one different step, which is a top-up correction for brain, which we currently don't do for the spinal cord, but I know a recent publication has done that and they have shown good results. So that might be one avenue to try as well. So this we do to correct for the distortions in the AP directions, basically in the phase encoding direction. So we get some volumes during our acquisition with the opposite. I know I'm being too technical, but with the opposite bullet polarity, and then we use that to correct for the distortions in the phase encoding direction. And similar to the spinal cord, we bring the white matter and CSF masks to the native space. Here we use FLIRT. Again, this is all FSL's functionality. And here I show the function for the white matter, and we basically do the same for CSF. Okay. This is how it would look. So this is our white matter and CSF mask in the native space, which we then use to regress the noise out. Exactly. So we extract the noise time series, and we don't use the mean, but we use this eigen option, which gives the first eigenvalue of the time series. And here you can see the output text file. Again, we do the PNM for brain as well. Here, there's a bit caveat. So because we acquire brain and spinal cord together, and PNM is slice-wise, we account for that within our pipeline. I'm happy to explain later if you have a question. But we do we basically regress out the physiological noise for the brain as well. Here is the file, the custom slice timing file that we create for our acquisition. And basically, after we do the denoising, we also bring our brain data to template space as well, because we both want our spinal cord data and brain data to be in the template space as well. And then finally, we feed all of this nicely denoised data to first level analysis. This depends on your task. In this case, as you may remember from the beginning of my presentation, this was a force matching task with the dynamometer, and we look at all these different contrasts, and you can see this nice group activation met for this particular subject in here for the brain and here for the spinal cord for this first contrast low condition.
Do you do denoising or anything just on the second from the upstream?
Yes, we first remove the noise and then we feed the denoised image to DLM.
Why image to noise?
So we use FSL for all of this, and so this is why I think this also we are doing this because I think it also allows, for example, easier functional connectivity calculations and so on to do this. And because we are also doing it in the template space. This is why, we first denoise the images in the native space, and then we bring the template space, and then we use the template space images for further analysis. This is why we don't do everything within one pipeline, because our noise regressors are in subject space.
Which FSL tool does that, regressing those?
Feed. Basically, it's a GLM model that you just regress the noise out.
I did consider that do you do AND-split extraction as well?
And for the structural, that's to get the functional brain mask.
And that is also brain extraction.
Yes, true.
And who
I think structural for that, in my experience, really left a lot of the skull, and for the functional, we don't need that exact delineation, but we use that mask to then further mask our like non-brain tissue.
The other question is,
so that would be the top up.
Is there anything similar
No, it hasn't been really tested out for spine yet. There is. So basically, if you are correct me if I'm not, so there's this distortion in the phase encoding direction. So one image looks like this, especially where there's a signal dropout, and the other image looks like this. Especially if you look at the frontal part of the brain, and this is supposed to correct for that.
One direction you see the pixel get stretched, one direction you see the pixels get compressed. So you try.
Yeah.
Yeah.
EP and the WI, I believe.
Yeah.
Uh-huh. So it hasn't been so far validated for the spinal cord, and I don't know if you have tried. I didn't try, but as I said, a recent group has used it. I can refer you to that publication, and they got good results. We have the same images for the spinal cord too. I don't know if we have really tried doing top up or not.
I can't remember whether I tried or not. But when I look at the spinal cord images, I think maybe it's smaller. Those distortion is less obvious.
was that
And I think also since during the registration we do non-linear registration, we kind of compensate for those distortion in the spinal cord during registration to template. So it's just adding extra steps.
something which came up yesterday also, like we do brain but so this is the top of that. It's inbuilt in it.
Yes, all of this except the ANTS tool is based on FSR. Yes.
Like this is this area on the brain is like
No, it's combined corticospinal acquisition.
I guess it's like the top of the now it's like the problem is the same, so like the same.
So we have the belief up, belief down for both brain and spinal cord as well, yes, because it's combined, but we just don't do it for spinal cord because it hasn't been very well tested and validated.
They apply the same field of view with the Olympia.
Yes. I mean, the brain and spine field of views are different, but it's a combined acquisition. So spine field of view is smaller, brain is bigger, but the acquisition is combined. Exactly the same, but just in another it's APPA.
So you do all your fMRI conditions in the up particle, and then you just acquire the full volume and stuff.
I guess we have the data.
We have the
Somebody
data.
wants to play around and explore. I'll do a top up there.
I have a question related to this. So when you acquire the data volume, data slice-wise from the brain to the spinal cord, do you alternate? Maybe her, this is the question related to her, but do you alternate between brain slice and spine slice, or do you do it?
We alternate.
At the beginning, I mixed the two together, like odd, odds, and then even. But then I because our TR is 2.5 seconds long, I kind of find that sometimes the spinal cord seems to like the physiological noise, the breathing cycle kind of change after 1.5 seconds. So then we switch to all odds and even in the brain, then odd and even in the spine. But you can do whatever you want if you have a justification.
I don't know how many slides is the data.
Well, 30 and 15.
Just for I know.
This is why we have a custom slice timing file, for example, because we don't like do the regular odd or interleave, so we know the slice timing and we input that to our slice timing or PNM to make sure everything is correct. And this
one volume time of acquisition for the entire volume.
2.5 seconds. We can probably push it a little shorter.
I was walking up with in the brain, typically at the very beginning with the API acquisition, they're like very like high, like what is it, like high value, and they goes to rapidly like the average like the signal, which is like many people like some people say like don't steady state, and then like our like usually discard like the first like 8 or some volume at the very beginning. Is that similar to the like the spine or fMRI data set too?
Yes, we get the dummy volumes, but I don't know if we just don't collect them. I always forget. I think we all forget.
Yeah, we also do we remove the first couple of volumes for the spinal cord as well. But I don't know how the steady state calculations work for spinal cord. We have like how many volumes should be removed from the spinal cord? Hmm, I see. Yeah.
Sequence sense, but don't save them.
Mm.
So you don't need to care about it. Yeah.
Well, even when they are domestic, but when you get more similar, then the very choose even they have.
I see.
So
I see. That's a good point.
that,
Also, for example, for our pain studies, we would also remove the first trial because they would be very shocked and surprised, and that would create so that there might be even a task-based reason for that too. So which brings me to the end of my talk, and you might think, okay, how do I ask these questions? There's no SCT for brain. I mean, FSL forum is good. I don't find it very user-friendly, but I recommend for the brain using the NeuroStars tool. And here you can see again a question I asked about a multi-site bits dataset, and I got a nice response from the team. And yeah, now we can dive in. Thank you so much for your attention. No, this was a long presentation, but I hope you learned something.